Welcome to the deep dive. Go ahead and turn the lights down a bit, maybe grab a warm cup of coffee and get comfortable.
Yeah, settle in.
We are definitely going for a bit of a late night radio vibe today because we are getting into the foundational architecture of the systems that are basically reshaping the entire tech landscape right now.
The absolute core of it.
Exactly. And look, if you are listening to this right now, we know exactly who you are. You are a software engineer. You build things.
You're not just looking at the surface level.
Right. You are looking to deepen your understanding of AI architecture. You don't just want to know, how to call an OpenAI API endpoint. You want to know how the engine actually runs under the hood.
Which is exactly what we have today. A really fantastic stack of notes covering a concept called masked self-attention.
Masked self-attention. And our mission for this deep dive is to understand not just the theoretical math of how information flow is controlled inside a transformer model, but the profound engineering and system-level implications of that math.
Yeah, we are talking about how a very specific matrix operation makes running modern large language models computationally viable in the first place.
Okay, let's unpack this, because to really appreciate the architecture here, there's this massive paradox we have to start with.
It is a huge paradox at the heart of how these systems are built versus how they are deployed. Think about the system state during inference.
When it's actually running in production.
Right. When a model generates text in production, it is a strictly sequential autoregressive process. It writes one token, appends it to the context, and uses that new state to generate the next token.
One by one.
One by one. It has absolutely no access to future state. But during the training phase, the paradigm completely flips. We feed the system massive, complete documents all at once.
In a single batch operation.
Exactly.
So the notes refer to this as the cheating problem, which makes sense. But looking at it through a systems engineering lens, this is essentially a massive data leakage vulnerability. Right?
Oh, 100%.
Like if we are processing a string array containing 1,000 words in parallel, the entire array is sitting right there in the GPU's memory.
Yep, all of it.
So if the model is currently calculating the weights for position 3 and trying to predict position 4, what stops the underlying matrix operations from just reading the memory address of position 4?
Nothing.
Yeah.
Inherently, nothing stops it. If you run a standard, unconstrained, bidirectional attention mechanism over that array, position 3 will absolutely access the memory of position 4.
It just looks ahead.
It reads the future token, incorporates it into its embedding, and the loss function for predicting that token just drops to 0.
Because it already knows the answer. It's like taking an exam with the answer key sitting face up on the desk.
That is the perfect analogy. The model won't learn the grammatical structure, the context, or the semantic relationships. It will simply learn how to execute a highly optimized memory pointer lookup.
Right, it just bypasses the entire optimization process.
Exactly.
So, okay, if parallel processing causes this catastrophic data leakage, why don't we just train the model sequentially?
Match the training environment to the inference environment.
Yeah. Why not just feed in the first word, calculate the gradient, feed in the second word, and step through the loop?
Because of the hardware layer. Modern GPUs are designed for massively parallel operations. CMD, single instruction, multiple data.
Right, you want to use all those cores.
If you try to iterate through a sequence using a sequential loop, doing a separate forward pass for every single token incrementally, you are essentially starving the GPU cores.
You're barely utilizing the hardware.
Barely. And the training time would scale linearly with the number of tokens. A model that takes 3 months to train in parallel might take 3 decades to train sequentially.
3 decades.
Wow.
Yeah.
The absolute brilliance of the transformer architecture is its ability to parallelize time. It processes the entire sequence in a single massive matrix multiplication, predicting the next token for every single position concurrently.
Which brings us back to the paradox. We need the massive computational throughput of a parallel matrix operation, but we need to strictly enforce the arrow of time to prevent that data leakage.
This raises an important question. How do we keep that speed without letting the model peak?
The sources point to the causal mask as the mechanism that solves this. It's also called a lower triangular mask. Walk us through the actual mechanics of how this enforces causality at the tensor level.
Let's visualize the raw attention scores before any masking happens. For the engineers listening, remember that self-attention is fundamentally a dot product operation.
You have a query matrix and a key matrix.
Right. The query matrix represents what a specific token is looking for, and the key matrix represents the context other tokens hold. When you multiply the query matrix by the transpose of the key matrix, you generate an n by n grid of raw relevance scores.
Where n is your sequence length.
Exactly. So if your sequence is 5 words long, you have a 5 by 5 matrix. In a bidirectional model, every cell in that matrix is populated with a value. Token 1 is attending to token 5, token 3 is attending to token 2, and so on.
So to enforce causality, we have to manipulate that 5 by 5 matrix so that any operation pointing to a future token is completely neutralized.
By the mask.
We take a lower triangular matrix. It's like a staircase pattern, where everything on and below the diagonal is kept and everything above the diagonal represents the future. It reminds me of the analogy in the notes about a staircase curtain in a theater, where each row can only see up to a certain act.
Or writing on a typewriter. You can see what you typed, but not what you haven't typed yet.
Right. But there is a very specific detail in these notes that stands out. When we block those future tokens above the diagonal, we don't just multiply them by 0. We set their raw attention scores to negative infinity.
Negative infinity.
Why that specific extreme mathematical value?
Because of where this mask is applied in the computational graph. You apply the causal mask before the raw attention scores are passed through the softmax function.
Ah, the softmax function.
Right. Softmax is a normalization function that converts raw, unbounded logits into a clean probability distribution that sums to exactly 1.0.
It forces everything to be a percentage.
Exactly. And to do that, the softmax function takes the mathematical exponential of every value in the vector, e to the power of x, and then divides it by the sum of all exponentials.
I see the architecture now. If we just set the raw scores to 0, the exponential of 0, e to the 0, is 1.
Exactly. Those future tokens would still carry a baseline weight.
They would totally corrupt the probability distribution.
Precisely. If you set them to 0, the softmax function will still assign them a slice of the probability mass, but the mathematical limit of e raised to the power of negative infinity is 0.
So by adding negative infinity to the future positions in the raw logit matrix, the softmax function just squashes them down to an absolute mathematical 0.
They are entirely eliminated from the attention weights. Position 3 will distribute 100% of its attention probability across positions 1, 2, and 3.
The computational pipeline maintains its parallel structure, but the data leakage is completely sealed. That is incredibly elegant. You are enforcing a sequential software constraint using a geometric shape layered over a matrix.
It really is beautiful math.
Okay, here's where it gets really interesting. Because the notes highlight that this causal mask isn't just a universal rule for all large language models. It's an architectural choice that dictates the fundamental behavior of the system.
What's fascinating here is that it acts as a control flow mechanism. The model weights, the heavy neural network parameters, the computation of the query, key, and value matrices, they are structurally identical across different transformer families.
The actual brains are the same.
The exact same. But the mask you pass into the function changes the entire nature of the program. The causal mask we just discussed is strictly for autoregressive models.
We call these decoders, like the GPT family.
Right. Their primary function is generation, which requires strict forward time adherence.
But if we look at encoders like the BERT architecture, they don't use this lower triangular mask at all.
They don't, because their objective function is entirely different. BERT isn't generating text left to right. It's a representation model designed to deeply understand a static document.
It's trained using masked language modeling, essentially a fill-in-the-blank API.
Exactly. You randomly hide a token in the middle of a sentence and ask the model to predict what was there. To optimize for that task, the model needs to analyze the surrounding context on both sides, left and right.
So you pass in a completely unmasked, fully bidirectional attention matrix. Every token attends to every other token.
You let it see the whole board.
This framing of the mask as a configuration flag is fascinating. You pass an empty mask. You instantiate an encoder that comprehends holistic document context. You pass a lower triangular mask. You instantiate a decoder that generates sequential text.
Just by changing the binary shape of a matrix.
But the sources also mention padding masks. In an enterprise environment, you are never just processing one sequence at a time. You are processing massive batches, and those sequences are never the same length.
That is a fundamental constraint of tensor operations. You cannot pass a jagged array into a CGA kernel. If your batch has one sequence that is 50 tokens long and another sequence that is 30 tokens long, you have to pad the shorter sequence.
You add 20 dummy paddy tokens so the matrix dimensions align perfectly.
Right. To make the matrix square.
But introducing 20 dummy tokens into the self-attention calculation seems like it would heavily pollute the mathematical embeddings. The model would start calculating the semantic relationship between the word database and an empty padding string.
It absolutely would corrupt the embeddings, which is why the padding mask is critical. It operates in the exact same principle as the causal mask. You generate a matrix that identifies the column indices of all padding tokens, and you inject negative infinity into those positions before the softmax function.
So the attention weights for the padding tokens drop to zero.
Exactly. The neural network computes the fixed-size matrices but mathematically ignores the filler data. And during training, you don't run these masks sequentially. You take the element-wise maximum of the causal mask and the padding mask, effectively combining them into a single constraint matrix.
Are there hybrid approaches? Say you were building a system like T5, which is an encoder-decoder model used for translation or document summarization. You have a prompt like a long article, and you need the model to generate a summary. Do you have to choose between bidirectional understanding and causal generation?
You don't, thanks to something called prefix masking. This is where the mask as a software program really shines. You can construct a custom mask matrix tailored to the specific API request.
So you mix and match.
Yeah. For the tokens comprising the input prompt, the prefix, you configure the matrix to allow fully bidirectional attention. The model can look forward and backward across the entire article to understand the deep context.
And then for the generation part.
For the section of the matrix corresponding to the tokens the model is actively generating for the summary, you enforce the causal lower triangular pattern. You seamlessly blend an encoder's comprehension with a decoder's generation capability.
Just by painting a different pattern of negative infinities.
Exactly.
So what does this all mean for the production side of things? Because this is where the real engineering challenges emerge. For anyone tasked with actually serving these massive models to thousands of concurrent users, the causal mask does a lot more than just prevent cheating during training.
Oh, absolutely.
It is the fundamental prerequisite for a technique called KV caching, key value caching.
KV caching is arguably the most important optimization in modern AI deployment. Let's trace the execution path of a decoder model during inference. It generates token 100. To do that, it computes the query, key, and value vectors for token 100 and calculates the attention scores against tokens 1 through 99.
And then it loops back around to generate token 101.
Right.
In a naive implementation, to calculate the attention for token 101, the system would have to recalculate the key and value vectors for all 100 previous tokens, pass them through the linear layers, compute the dot products all over again.
That scales at O of n complexity for every single step. For a long context window, that would instantly throttle the compute cluster.
Instantly.
But here is where the causal mask pays its ultimate dividend. Because the causal mask enforces strict left-to-right flow, we have a mathematical guarantee. Token 50's attention output depends entirely and exclusively on tokens 1 through 50. Token 50 will never, under any circumstances, look at token 100.
Because the negative infinity boundary permanently blocks it.
Right. And because of that immutable boundary, once token 50's key and value vectors are computed, they are completely static. They will never change for the rest of that generation cycle.
Therefore, we don't need to recalculate them.
We can write them to a cache in the GPU's memory. When the model moves on to generate token 101, it only computes the query, key, and value for that single new token. It pulls the key and value vectors for the previous 100 tokens directly out of the cache.
So we are transforming an O of n matrix operation per generation step into an O of 1 operation plus a memory lookup.
A massive optimization.
You've slashed the compute requirement by orders of magnitude. Instead of doing 1,000 full forward passes to generate 1,000 tokens, you do one massive forward pass for the prompt and 999 incredibly cheap incremental lookups.
That transformation is the bedrock of real-time LLM inference. Without the causal guarantee enabling the KV cache, modern applications like ChatGPT or GitHub Copilot would be too slow to be usable. They speed up inference by 10x to 100x.
But wait, let's look at the infrastructure cost of this cache because it's not a free lunch. We are trading compute cycles for VRAM footprint.
Yeah.
If we are caching the key and value vectors for every single token, how is that sustainable?
It's the primary bottleneck right now.
Let's say we have a model with 80 layers and 64 attention heads. You're storing high-precision floating point numbers for every single token across every head and every layer. As the context window grows from a few paragraphs to tens of thousands of words, that cache has to expand linearly.
It does, and that is precisely the memory wall that infrastructure engineers are constantly fighting. The model weights are static. If your model is 70 billion parameters, it takes up a fixed block of VRAM. But the KV cache is dynamic state.
It grows with the batch size and the sequence length.
Exactly. If you are serving thousands of concurrent users, the KV cache can easily consume more GPU memory than the model weights themselves.
Which explains the out-of-memory exceptions that are notoriously common when deploying these systems.
Yes. When you hit an ORM error during inference, it's rarely the model weights. It's almost always the KV cache exceeding the physical limits of the VRAM.
It's just massive.
This bottleneck is driving the most aggressive research in the field right now. Engineers are developing techniques like multi-query attention and grouped query attention, which reduce the cache size by sharing key and value heads across multiple query heads.
I've also seen research into page attention, which treats the KV cache like virtual memory pages in an operating system to reduce fragmentation.
Right, but all of these optimization frameworks are fundamentally built on top of the causal guarantee provided by the lower triangular mask.
I want to dig into the actual code implementation for a minute based on these notes. If a developer opens up the source code for a transformer model in a framework like PyTorch, how are these masks actually constructed and applied? I assume they aren't iterating through nested loops and writing if token index A is greater than token index B conditional statements.
No, absolutely not. Branching logic like if statements is the enemy of GPU performance. A CUA kernel wants to execute the exact same instruction across thousands of cores simultaneously. If you introduce conditional branching, you force the hardware to serialize the execution, destroying your parallel speedup.
So how do you apply the mask without branching?
You rely on highly optimized, low-level tensor operations. PyTorch uses a function called torch.triu, which stands for upper triangular. You instantiate a tensor of the desired sequence length filled entirely with negative infinity. Then you use torch.triu to extract just the upper triangle of that tensor, replacing everything on and below the diagonal with zeros.
So you essentially pre-compute the constraint matrix.
Exactly. You generate this constraint matrix once per sequence length. Then, during the forward pass, you take your raw attention scores, which took heavy matrix multiplication to generate, and you simply perform an element-wise addition.
Just add them together.
Add the constraint matrix to the raw scores. The positions with 0 remain unchanged. The future positions have negative infinity added to them. It's a bulk vectorized addition operation with 0 branching logic, executed in fractions of a millisecond on the hardware right before the softmax function is called.
It's a masterclass in aligning software architecture with hardware constraints. Before we wrap this deep dive up, I want to address a couple of common misconceptions the sources highlight regarding masked attention. These are easy traps for developers to fall into when conceptualizing the system. The first is a mental model error. People hear the word masking, and they assume the algorithm is literally dropping or deleting the future tokens from the sequence array.
That is a critical distinction. The tokens are not deleted, and the array size does not shrink. The tensors must maintain static dimensions for the hardware to process them.
Right.
Token 5 is still sitting in memory. It still possesses a high-dimensional embedding vector. The mask doesn't erase the data structure. It simply forces the mathematical relationship, the attention weight, between token 3 and token 5 to 0. Token 5 becomes functionally invisible to token 3's specific computation layer, while remaining perfectly intact for its own calculations later in the parallel pass.
The second misconception deals with the model's predictive capability. The question often comes up, if we are strictly preventing the model from seeing the future during training, how does it actually learn to anticipate what comes next in production?
It's important to separate the concept of peaking from the concept of learning. The causal mask prevents the model from peaking at the specific granular answer key of the current training batch. It forces the loss function, to be honest. But the model is processing trillions of tokens across millions of documents.
So it's seeing the patterns.
Exactly. When it sees the sequence the backend server returned a status code of, it doesn't need to cheat and peek at the next token to anticipate the output. It has mathematically encoded the statistical probability distributions of network protocols. It knows that 200 or 404 or 500 have overwhelmingly high probability masses in that specific semantic context.
It anticipates the future not by looking ahead in the array, but by resolving the complex statistical patterns of the past. Let's recap the engineering journey we've taken today. We started with the paradox of needing parallel throughput for training while preventing the catastrophic data leakage of position 3 accessing position 4's memory. We solved it with the causal mask, a lower triangular matrix that enforces strict sequential logic onto parallel tensor operations.
We dug into the math, specifically how injecting negative infinity before the softmax function mathematically guarantees an absolute zero probability for future tokens.
We looked at how swapping this mask completely alters the API, turning encoders into decoders. And finally, we traced the massive downstream impact of this math, how the causal guarantee unlocks KV caching, turning an O of n operations bottleneck into an O of 1 cache lookup, while simultaneously introducing the VRAM memory boundary that infrastructure engineers battle today.
If we connect this to the bigger picture, it really is a profound piece of system architecture. You're taking the most complex, high-dimensional probability engines ever built, and you are steering their fundamental behavior using the geometric shape of a constraint matrix. You aren't writing nested logic loops. You are shaping the flow of information through pure mathematics.
It's brilliant. And as you close your IDE for the night or finish up your commute, I want to leave you with one final thought to mull over. The causal mask we spent this entire deep dive discussing acts as an uncompromising filter. It sets hard boundaries of negative infinity to dictate exactly what information the model is authorized to access. It guarantees the past cannot see the future.
Right.
But once those strict boundaries are drawn, once the algorithm authorizes the past tokens to interact, how does the system dynamically decide how much to care about the tokens that remain? The mask just outputs a binary authorized or unauthorized. But inside that authorized window, what is happening inside the mathematical engine when those raw unmasked dot products get processed by the softmax function to allocate the actual probability mass?
That's the real magic.
Exactly. The mask dictates the constraints, but the attention weights handle the focus. And the mechanics of how that focus shifts dynamically across a sequence might just be the most complex mechanism of all. Thank you for joining us on the deep dive. Catch you next time.